Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello everyone. Yeah, welcome. It's a great pleasure to introduce Samir Kuller from University of Maryland. Samir has done very nice work on basic algorithms and approximation algorithms, but today he's going to tell us how they're related to scheduling to minimize energy. Yeah.
Thanks, Mohit. I have a lot of slides today, and I know it's Friday afternoon, it's late. So please feel free to interject, ask questions, and also it's fine if I don't get through everything, and I'll try to keep it light on proofs. So this is work that I've been involved in for several years and joint work with several people who I'll show you pictures and give you names at the end. So I'm going to try to cover a bunch of results, and this work was started about 5 years ago. And the motivation for our work was trying to understand some scheduling problems dealing with data centers. So as we know, data centers are everywhere these days, consume a large amount of energy. So a couple of points I wanted to notice was that the workload actually fluctuates over time. And so you might actually begin to ask fundamental questions like, maybe we can save energy by shutting down a large fraction of the machines when they are not in use. And these days, servers themselves are getting more efficient about energy usage. So your cell phone processor, for example, can go into sleep mode, power save mode, running on a battery. So energy savings is very, very important. More importantly, I want to talk about the energy consumption is obviously very huge, and there are thousands of processors in a data center, and each one is consuming significant amount of energy. And we are looking at sort of scheduling policies up at the CPU level. Now, more broadly, you could say, well, I have a large set of disks, and maybe I could shut disks down as well to save power, and then there's costly expenses in bringing them back up. But in CPUs, it turns out that overhead of turning things back on is much lower. You can put them into different kinds of sleep states, but you can go into sleep states where you can rapidly recover from, but you're still consuming a lot of energy if you slow down the processor. Okay, so obviously I'm an algorithms researcher, and we're going to look at problems which have to do with scheduling, where you have a large collection of jobs that you want to do, and we sort of want to now examine that question with this property. We now have an ability to turn machines on and off. So if you think about sort of scheduling, the literature goes back 50 plus years. Most standard scheduling problems, you're given jobs and you're given some machines or resources, and you have to figure out ways to run these jobs on those machines. And most of the work historically is done from the jobs perspective. So we've asked the question, the machines are always on, we don't really care about how much energy they are using, but I want to run these jobs so that there's high job satisfaction, or the clients that are issuing these jobs, they are happy with the services. So happiness might be, I want fast response time. I want these jobs to complete quickly. Nobody really worries about the machine's perspective, right? But there's a very interesting trade-off that we're trying to understand, that maybe at a slight cost to happiness of jobs, maybe we can cut the energy usage significantly. Right? So there's clearly a trade-off. If you have unbounded energy, then you said you can maximize job happiness, but in general, we want to keep the energy costs into account. So our goal is to sort of look at both online and offline problems in the space. Today's talk is mostly going to focus on offline algorithms. So these are algorithms where you know the entire input in advance and you're trying to compute some solution in advance. Clearly, in terms of real world scheduling, that's not the whole picture. You have jobs that you know about and you find a schedule, and then there'll be jobs that you don't know about that will arrive at the last minute and will need to be fitted into a schedule. So I have some more recent work that I won't get time to talk about on online algorithms as well. And then there are some cases, special cases for which we can derive optimal polynomial time solutions, and then there are other cases where the problems themselves are NP-hard. And then our goal is to develop approximation algorithms. There's a lot of experts here in the room in the first row who work on this topic, where our goal is to develop algorithms that run in polynomial time, but might not find optimal solutions, but we're trying to prove that these solutions are close to optimal. Okay. So one other piece of work from 2010 that motivated us was an Intel internal technical report which talked about power-aware job scheduling. And they sort of highlighted the fact that job scheduling hasn't been studied with this power or energy constraint in mind. And there's a large bunch of research on this topic called batch scheduling. So what is batch scheduling? Batch scheduling, the idea is the following, that groups of jobs in one batch can be scheduled at the same cost as one job. Right? So you might have an upper bound on the batch size. It's sort of like saying, well, I want to drive to downtown Seattle, my car can take 7 passengers, and whether I take 1 passenger or 7 passengers, the cost is the same as one trip to downtown Seattle, right? So that's what a batch consists of. And in a lot of the literature on batch scheduling, people had mostly focused on finding feasible schedules by completely ignoring the energy cost. And so one of the things that we looked at was how do we optimize for energy. And I'll get into this in more detail in a few minutes. So let me start off by talking about one sort of classical problem and one twist to it that we looked at a few years ago, which was the starting point of some of this research. So there's a very famous problem studied for about 25 years called unrelated parallel machine scheduling by, I guess, starting from the work by Lenstra, Schmois, and Tardosh. So here the framework is the following. You're given a collection of jobs, J1 to Jn, which are shown by the red nodes on the left-hand side. And then you're given a collection of machines, M1 to MM. And these jobs, these machines are not identical. So what it means is that some job might run very quickly on some machine and might be very slow on another machine, or might even be infeasible to be running on another machine. But still, the goal is to somehow assign jobs so that we minimize the maximum load on any machine. So you want to sort of do a load balance solution. And they gave some very nice algorithms, even though the problem is NP hard. Okay. So the one sort of generalization of this problem that we looked at was the following. Now, let's assume that these machines are sort of available, but you have to purchase them. So each machine has a buying cost. So machine MI has a purchase cost of CI. So it's like sort of saying I go to the marketplace, I have lots of jobs I want to run, lots of machines are available, but I have some fixed amount of money that I want to spend, and I now want to decide which machines I want to buy. So I have some budget that I'm given C, and I want to choose a subset of machines that I buy that fit within my budget. And now, once I have chosen the set of machines that I buy, now I have a job scheduling problem because I know what the set of machines is, and I want to schedule all the jobs on those machines. So the goal is to determine this subset of machines with cost at most C, and then assign the jobs to the machines so that we minimize the maximum load. Okay, so that's what we call the machine activation problem.
So this basically the cost is just pay up once per machine. It's not how many per job or something. That's
right. The cost is just to buy the machines in advance, right? So, you'll see this analogy a little bit later. But later on, if I have one machine, I could think of this vertical axis actually as time. So I might say it's the same machine, but whenever I turn it on, I'm paying some cost. So there is a relationship between time and that. But even though in this model, it's sort of just saying I have a bunch of jobs, a workload that I want to run, I can decide what machines to purchase. I have a budget, which machine should I buy, right? And of course, this problem in this way actually turns out even it generalizes the famous set cover problem, right? Because I can think of these jobs as elements and these machines as sets, and then I'm choosing certain sets to buy. And then maybe if a element belongs to a certain set, that job can be scheduled on that machine, but its load is minimal. If the element is not in a certain set, then its workload is very high, right? So this framework that I just described actually captures both the unrelated parallel machine model when all the CIs are 0, and it also captures the famous set cover problem for which no approximation algorithm better than log n is known, right? So the result that we proved, this is joint work with Jian Li and Barna Saha in paper in Sura 2010, is sort of you kind of get the best of both worlds. So we showed that if you fix a budget of C, and suppose there's an optimum solution that meets the budget of C and has max load T, then we can find a solution with cost C times log n with a max load of 2T. So and both of these sort of log n and 2 are sort of unavoidable because of the special cases, right? And so I won't really go into the algorithm. I just wanted to say that this was sort of the motivation for studying this kind of cost problem. And then you can think of, if you think of this sort of as jobs and you think of this as time, edges might go to certain machine being on at a certain time if the job can be scheduled in that slot, right? And the edge is missing if it just can't be scheduled. So now let me move to even a much more simpler model where talking about batch scheduling. So this is like a shipping problem. So we have a container that has to leave the port. This is the available time or the release time of the job. And then there's a deadline by which the container has to arrive at a certain location. And we have sort of multiple jobs, right? So I have another container that's going to be ready at a later time, and then is expected at some deadline. So we think of this as simply as jobs having release times and deadlines. And the ship is sort of like this batch machine that whenever I schedule the ship departing, up to a certain number of packages can be sent on the ship. So if I schedule the ship here, then I only do one job and the ship goes once. If I schedule the ship here, I can do both of these jobs. But of course, I cannot do an unbounded number of jobs. The ship has a capacity. So that's what I mean by the notion of batch. And so the question really is, what is the smallest number of trips necessary to schedule all these jobs so that you don't miss any deadlines, right? So that's sort of a very simple basic model that you can think of in this batch scheduling work. And prior work looks at this problem, but doesn't take into account the number of trips. The whole goal is just to find a feasible schedule with an unbounded number of trips. So one of our goals was to find an optimal solution for this problem. So I also wanted to say that this problem is a little bit more nuanced. So the shipping model is also known as the trucking model in the literature, where the batch has to be synchronized, right? So the jobs are scheduled in exactly the same group. You could think of another pizza oven model, which is slightly different, where I put a pizza in the oven, and then I put a second pizza in the oven, and then when the first one is finished, I can take it out and put another pizza in, right? Maybe 2 pizzas can bake simultaneously. So this is like a non-synchronized model. So this is a batch, but it's not a synchronized batch. It just has the property that at most 2 things are running at any point of time. And here we want to minimize the running cost or the energy cost, which is when the machine comes on and when the machine goes off. Okay, so is the distinction between these 2 models clear? Right? So in some sense, the model on the right is a bit more constrained because all the jobs have to be scheduled simultaneously. Okay. So I'm now going to get into this problem a bit more formally. So the problem that I just described is the following. I have n jobs. Each job has a release time and a deadline. In the most general version, we can think of a job as having some length. I'm going to focus for the next 10 minutes on unit length jobs. We have a batch machine, and it'll make life even simpler. I assume time is slotted, so I can, in a time slot, turn a machine on or off. And so if I turn the machine on, then we say that the machine is active, and I can schedule up to some number of jobs. And the whole goal is to minimize the number of active slots. That's very, very easy problem to think about. So you can think of this simple model as basically talking about maybe a rack of processors that I turn on, then a bunch of things can be done at the same time, or a multi-core processor where the processor is on and a bunch of threads can be executed simultaneously. Okay. So since I was going to talk about unit length jobs, so this example shows you a simple schedule, right? So here, if you look carefully, notice that the batch capacity is 3. So I have a schedule where each job here could have been scheduled at any point of time. And we have to align these jobs in a way and find a schedule so that I'm scheduling no more than B jobs at any point of time. So that's my batch capacity. And I'm trying to simply minimize the time slots for which the machine is on. In some sense, you could think of that as a projection on the x-axis of wherever you put these rectangles. Okay. So the question is now, how do we find an optimal solution for this problem, right? Now there is a general problem, famous problem known as capacitated set cover. So what is capacitated set cover? So it's generalized set cover in the following way. So I have a collection of elements and I have a collection of subsets. The subsets have some cost that you can pay to buy the set, but now it also comes with a capacity. So when I purchase a set, I cannot cover all of the elements in that set, but I have a restriction of how many elements I can cover. And I have some flexibility. So if this set has size 3 and costs $2, when I buy this set, I can cover any 2 of the 3 elements, but I can't cover all 3. Okay. Now, capacitated set cover has been widely studied and has actually many, many applications itself. It's an NP-hard problem. And there's some very interesting work by Woolsey that I'll mention in a second. But what is the relationship with our scheduling problem? So I could think of every time slot as a potential set, right? So turning the machine on is like buying that set. And then all of the jobs that overlap or intersect the time slot are elements of that set. But of course, the point is if I turn the machine on here, I cannot cover all of them, right? I have some capacity constraint. So you can think of this problem as a special case of capacitated set cover. But that's not very useful because capacitated set cover is a very hard problem. So there's a famous algorithm by Woolsey which gives a very simple conceptual greedy approximation, but the bound is not so good. It's an order log n approximation. But of course, that maps it to a hard problem, right? So, but the problem, the scheduling problem itself is not NP-hard. So in 2008, there was a paper that showed that you can solve the problem optimally using dynamic programming, but the running time is high, the complexity is high, okay? So it's polynomial, but high. So the next question you can ask is there a faster exact algorithm, right, without using dynamic programming? So that's the algorithm that I was going to present next. The algorithm itself is called lazy activation. And this is joint work with Jessica Chang and Hal Gabow. And so here's how the algorithm is going to work. So is there any questions about the problem itself?
There's no cost over here, right? Is there a cost involved? Like, oh, sorry, so cost was
just when you turn the machine on or off, there is no cost, right? That's a good point. So it's quite likely the dynamic programming solution is easier to extend in the general cost model, which is a non-uniform cost. So what Mohit asked is maybe it's more expensive to run a machine during peak energy times and maybe cheaper to run at later times, and we don't model that, right? For us, turning the machine on is so certainly, yeah. So their dynamic programming, I'm sure, can be extended to handle costs. So let me describe the algorithm. The algorithm is very, very simple. So the algorithm is called lazy activation. So the idea behind lazy activation is that you never have to be in a rush to do jobs, right? If you do jobs as soon as they are released, then you are not really overlapping them in the maximal possible way. So lazy activation just says I should basically do things lazily as late as possible. So you could think of a lazy activation algorithm which says, let's look at the first job who has the earliest deadline. There's no reason to do this job before this deadline, so we'll schedule it here. But once I turn the machine on to do this job, now you have an option of what other jobs you want to schedule, right? There's a whole bunch of other jobs that you could schedule at this point of time. And so obviously I've only scheduled one job. I have up to a capacity of 3, so I could schedule 2 more jobs. And what the lazy activation algorithm does, it says take the jobs that are earliest in deadline in the future and schedule those first, right? So that's sort of the optimal, we can prove that that's sort of the right thing to do, right? The problem with this algorithm that I just described to you doesn't quite work. And the reason it doesn't quite work is that you might be running along and you might get stuck. You might get stuck because you suddenly come to a point in time where maybe 100 times B jobs have that deadline. And so now you just don't have enough time to schedule all the jobs, right? Because you sort of waited too long and not all of them can be scheduled here. So we're going to have a pre-processing step. In the pre-processing step, we're going to do the following. So I'm going to run this pre-processing step before we start lazy activation. Now I'm going to look at all of the jobs and I'm going to scan time right to left. Okay. So I'm going to look at the last deadline, for example, and ask the question, how many jobs have this common deadline, right? So if at most B jobs have this common deadline, then we are not worried. In fact, that's the property we want to enforce. We want to enforce that at every deadline, possible value, there are at most B jobs with that deadline, okay? So now the question is, what do we do if we have more than B jobs with this deadline, right? So in this example, B is 3, but we have 5 jobs with that deadline. So obviously the optimum solution cannot schedule all 5 jobs in that last slot. There's an upper bound of 3. So what we're going to do is we're going to take all the excess jobs more than B that were released the earliest possible and adjust their deadlines by subtracting 1, okay? So now certainly I have the property that at most B jobs with this deadline, and now we'll move to this value and enforce the same property again. So it might have been true that at this point of time there were less than B jobs with that deadline, but now I have more, and then we'll apply the same rule and apply this rule recursively, okay? So that's basically the entire algorithm. So in step 1, we do this pre-processing step where we scan the deadlines from right to left, and then in step 2, now we do the algorithm left to right doing lazy activation, and then every time I have some option of what to put, I'll pick the jobs who are not imminently due, but that one have the earliest deadline in the future, right? So a simple example is, suppose step 1 has been run, then I pick the job with the first deadline, I schedule that, and then all the among overlapping jobs, I pick the remaining 2, and I schedule those with the earliest deadline. I get rid of them and keep going, okay? So that's the entire algorithm. So the algorithm is very simple, very easy to implement. There's some interesting properties about the algorithm that are not completely obvious. So I won't really talk about the proof of the algorithm. The proof is not very complicated, you can work it out. But the not obvious property is the following. So here's an interesting case. Here again B is 3, but we have 7 jobs, all that are valid only over 2 slots, right? Now there is no way that we can do 7 jobs in these 2 time units if I can only schedule 3 jobs in 1 slot, okay? So of course this input instance itself is infeasible. There is no way that we can do 7 jobs in 2 time slots if I have B equals 3. Now what will happen in step 1, notice that I have 4 jobs with this deadline. So we'll subtract 1 from these 2 jobs. Now I'll have 4 jobs with this deadline, and then I'll subtract 1 of them again, and this window will collapse to the empty set, right? So this jobs window will collapse. So obviously this job has to be dropped. What is interesting is that we can prove that the algorithm actually schedules a maximum number of jobs that could be scheduled in any optimum solution. Moreover, the number of slots for which the algorithm is turns the machine on is optimal. Okay, so that's the part that actually takes a little bit of work to prove, that we are scheduling the largest number of jobs that can feasibly be scheduled, but also at optimal cost. Okay, questions? So in the next part of the talk, I want to sort of talk a little bit about arbitrary length jobs, and there are some interesting open questions here. So in arbitrary length jobs, these are jobs that are not of unit length. So here in this example, I have jobs, 3 jobs, release times, deadlines, and some processing time. And this is the non-preemptive case on the left, right? So this job, once I start it, I have to run the job all the way to completion. So in this case, in this example on the left, the active time of this machine is 4, right? So the machine is turned on for the first 3 slots, then it's turned off for 2 slots, and then I have to do the last job. But if I'm allowed preemption, then we could do interesting things where this middle job, I do 2 units of the job, I stop it, and then I finish 1 unit later. So I could save a little bit on the active time by allowing for preemption. Okay. So it's sort of like saying that some things in the oven need to bake for longer, but interrupting that, I mean, I don't know whether I want to eat a pizza that got pulled out of the oven halfway being baked and then got put back in, right? But you could imagine processing of jobs, it could be interrupted for no cost. So this problem itself is NP hard. This is very easy to prove, the non-preemptive version. It turns out in the preemptive case, we actually don't know whether it's NP hard or not. Okay. So is the question clear? So they have jobs, release times and deadlines, arbitrary lengths, preemption is for free. I can schedule up to B jobs simultaneously, and I want to find an optimal schedule, which minimizes active time. We don't know whether it's NP hard or not. Okay. So our focus was for a long time on trying to identify a polynomial time solution for this problem, because we weren't sure it's NP hard and we couldn't prove that. So we were unable to find an optimal solution. So we developed an approximation algorithm, which I'll give you the high level ideas for. But again, it's an approximation algorithm without having a proof that the problem is NP hard. So there might actually be an optimal solution, or it might be NP hard, we don't know. Okay. So let me talk change gears a little bit and talk about a relationship with maximum flow, which some of you might not have seen before. So the maximum flow problem is a flow problem in a directed graph where I have a source and a sink, and we want to push the largest amount of flow from the source to the sink. So here we have a source and a sink. For every job, we're going to create a node in this graph, and the capacity of the edge going from the source to the job is simply the processing requirement of that job, right? So if this job has length 3, somehow 3 units of flow will reach this node and somehow have to be sent back to the sink, and all 3 units have to be scheduled. For every time slot itself, there's going to be a node here, and the capacity of the edge going from the time slot node to the sink node is simply the batch capacity B. At most B units, if I turn the machine on, at most B units can be scheduled there, right? Now in standard flow problems, the whole network is known and you just want to push maximum flow from S to T. So here the problem is slightly different. I want to select some of these time slots to activate, right? And once I activate a certain time slot, then I get a capacity of B going from that node to the sink node. If the time slot is turned off, then this capacity is 0, I cannot schedule anything there. So the whole goal is now is to select a subset of these nodes and then turn them on so that the max flow has a value which is the sum of the processing times of all of the jobs. So everything gets processed. Okay, so that's exactly the problem that we wish to solve here. Okay. So once I can decide a schedule for or subset of to turn on, then it's a flow problem. So I can certainly check feasibility of a schedule by solving a max flow, right? So if I decide, oh, I want slots 1, 3, 5, and 7 on, then the flow will tell me what the schedule is in a preemptive way. Okay. So, and we're going to use this oracle as a very simple algorithm now. So that leads to the concept of what I call minimal feasible solutions. So what we're going to do is we're going to turn on all of these slots initially. So we obviously know there's a feasible max flow if a feasible schedule exists. Then in arbitrary order, you pick the order, we'll just start turning these off one at a time. And if I turn it off, that's a permanent decision. All I want to check is turning it off still leaves a feasible max flow. Okay. So that's the algorithm, right? So it's just finding a minimal feasible solution. So we just shut down active slots one at a time, and we don't shut an active slot down if it's going to lead to infeasibility. So that's the entire algorithm. Okay. So start from all possible slots being active, and as long as a feasible solution is possible, we shut the slot down. Okay. So it turns out that this simple algorithm, which is really a dumb algorithm in some ways, not being intelligent in what order you're shutting things down, If you could find the right order, then you'll converge to an optimal solution. But being completely blind, we can actually prove that the cost of the solution is no more than 3 times opt. Okay. So this simple algorithm will find you a schedule which might not be optimal in terms of the number of active slots, but we can prove that its cost is no more than 3 times opt. Now, that bound of 3 is also in fact tight. So there are examples where if you are not careful in the order in which you shut things down, you could actually end up with a solution which is 3 times opt. So I'll show you one simple example illustrating a bound of 2, and then you can generalize this to a bound of 3. So here's a collection of jobs with release times, deadlines, and then the number on the right shows you the length of the job or what the processing needs are. Right. So here's an optimal solution. So this is an optimal solution where b equals 5, and this solution sort of has some interesting properties. These jobs, notice that are of length 4 and they're all rigid. So these jobs have sort of no option. So the machine really has some spare capacity here to do one thing at a time. And what we decided to do was to make progress on the long job, which is the sort of the right thing to do. But if you try turning the last slot off, it turns out that's feasible, right? So if you turn this last slot off, then it pushes these unit jobs, striping them across like this. So all these jobs get done, and then the long job gets pushed out. And that's a feasible thing to do. But shutting that last slot down is a big mistake, right? So that's, in this example, it's going to force the minimal solution to be factor 2 away from the optimal. Okay. So let me give you some high-level ideas about where this bound of 3 comes from. So let me forget this left shifting part. I'm not going to have time to discuss it. It's not really that crucial. But once we find a schedule in the end, how are we going to analyze it? There are some time slots in which I'm actually doing B jobs, right? So we found a schedule by this naive algorithm. There's some time slots for which we are doing B jobs, and there are some time slots which we call non-full slots where we're doing less than B jobs. Now, this kind of active time slot is great, right? Basically, I turned the machine on, the machine had a capacity of B, and now it's being 100% utilized, right? That's great. So we cannot have more than opt many of such slots. The problem comes when we have many, many slots of this type, where the machine had a very high capacity of B, but we were doing very little work. And so we might be paying sort of a heavy penalty there, right? So after the algorithm ends, the main thing is to come up with looking at the schedule and identify which slots are full and which slots are non-full. And then we sort of have to figure out how we're going to account for these non-full slots. If there's a large number of non-full slots, I want to sort of prove to you that they were unavoidable, and the optimum solution also has to have a very large number of idle slots where not much was happening. So that's the dichotomy of active slots by full and non-full. So here's sort of an example that gives you some intuition of what is going on. So obviously the proof is a bit more involved, but here's a good way to think about the intuition. Suppose this was the entire input, right? So this job had 3 units here, this job had 1 unit here, this job had 3 units there. And all the slots that you come up with are non-full, right? And you say, well, this is sort of unavoidable. What else could we Optimum do? There's no way to sort of piggyback and do multiple things, even though we had a batch capacity of B. So our whole goal should be to identify some subset of jobs, J star to charge, which are a disjoint collection of jobs, right? If I find a disjoint collection of jobs, all of which are pretty long, then the sum of the lengths of the jobs is sort of a lower bound on the number of active slots for any schedule. Agreed? Right? So if I tell you that these jobs are all disjoint in time, then I have to do them. The optimum solution has to pay that cost. Okay. So sadly, we could not find this subset J star. What we were able to find is a subset J star of jobs where at most 2 of these overlap at any slot. So it's not purely disjoint. It's a subset of jobs which have the property that if you look at any point of time, at most 2 jobs overlap at that point. So now if you think about the optimum schedule, the best thing that the optimum could do is have done 2 jobs, right? And what we can prove is all of our non-full slots don't exceed the sum of the lengths of the jobs in the subset J star, right? So that's where sort of the factor 2 comes from. And because we didn't worry about counting for the full slots, we sort of could be expending as many as close to opt slots there, right? So that's sort of where the bound of 3 comes from. Question?
Can you do a dual fitting argument?
So the algorithm would have to be modified, right? Because we have examples where this minimal solution, asymptotically as B gets large, is getting close to 3B, right? So the algorithm is sort of tight, right? No, so the algorithm.
Just to, alternative proof for the factor of 3 by dual fitting. just interpret the algorithm.
Quite likely, yeah. We didn't think about duality, but if you think about this disjoint argument, it is sort of a combinatorial, simple combinatorial argument, right?
So alternate algorithm would be just close down the slot, which is the least node, which does the order you check.
We apply no rule in the order. So I do believe still that there should be a combinatorial 2 approximation, which intelligent orders, as Mohit indicated, would be the right way to go, but we were unable to prove it. So now the problem does have a 2 approximation. So I'm not going to really have time to discuss it, but in the paper that appeared in SPA 2014, so this algorithm is based on LP rounding. So we basically write an integer program which is very similar to facility location type problems where you define a variable y sub t which models whether or not that slot is active or not active. And if a slot is active and yt is 1, then it gives you a certain processing capacity of b. You want to make sure that all the jobs get done, and all the jobs are processed, and now you get a fractional solution. So I have a picture of a fractional solution. I won't talk about the rounding, but that's what a fractional solution might look like. And then we have to round that to an integer solution, and you can get a 2 approximation this way, but it's pretty involved. So if you could get a cleaner combinatorial algorithm, I would be much happier with that. Okay. But the algorithm is actually quite slow. So Jessica actually implemented the algorithm, the flow-based one. And so in practice, there are a lot of rules that you can use, right? So for example, when I showed you the example where I said, oh, if I shut the slot down, the resulting flow is still feasible, so it's okay to shut it down. But if you notice, when that long job got ejected out into the open, the cost of that schedule was very high in terms of activation, right? So when we are solving this flow problem, we can actually try to compute some notion of a cost of this active schedule. And so you can use some heuristics to sort of guide your search and choose this slot versus that slot, which might be in the direction that you were alluding to. So in practice, that does very well. But it's slow because at every step, we need to solve this flow problem, right? It's not really incremental. So at every step, we are deciding which slot to shut down. So you might realize shutting this slot down is going to lead to infeasibility, so I don't touch it. I go to another one, I try it. Right? So the algorithm is slow because we have to solve these flow problems repeatedly. It's not a very fast algorithm. And the same problem happens with Woolsey. If you try implementing Woolsey, it's again not a very fast algorithm. Okay. So coming back to this idea of covering and this flow viewpoint, I think this is sort of an interesting problem, right? So you have a flow network. This sort of models the jobs like I described before. And then we have nodes here, and there's a capacity going to the sink. And in this active time scheduling, rather than computing a flow, what we're asking is I want to select a subset of the nodes on the right, and we pay for how many nodes we select. Then every time we select a node, we get a certain capacity of b. And then we're trying to find a flow that supports a certain value, right? So you can think of that as being another way to model active time scheduling, right? Now, this is a very general framework, right? And in fact, lots of problems can be thought of in this framework. So if you go back and look at a lot of work on vertex cover. So vertex cover is a classical problem which says I have a graph and I want to select some vertices to cover all of the edges. It's a covering problem. There's a problem for almost 10 years. In fact, Safi's here. He had a very nice paper on capacitated vertex covering. But the idea is that nodes now have capacity. So when you select a node, this node might have 100 edges incident on it. But if its capacity is 15, you can only cover 15 of those edges. Right? It's exactly a capacitated covering problem. So you could think of all of these capacitated covering problems that have been studied in the light of this way, in this flow network, right? So these nodes here are modeling edges of a graph. And then if this edge is incident to 2 vertices, it has a possibility of being covered by that node and being covered by that node. And the vertices of the graph are here. And now picking a vertex cover is just like selecting nodes on the right with a certain capacity. In the vertex cover case, in fact, this capacity is not even uniform. Every node has its own capacity. And then we want to route a certain amount of flow or assign all of the edges, right? And then all of these papers basically develop constant factor approximation algorithms for this problem, but there's some special structure. So in the graph case, these nodes have bounded degree exactly 2. We generalize this to hypergraphs where these nodes have constant degree and get constant approximation. Last year in SODA, there was a very nice paper by Cheung, Gumans, and Wong where they improved the bounds significantly. But all I was trying to point out was that all of these problems can be thought about in this general flow setting. And this problem, if you look at Gary and Johnson, actually has a name. It's called min edge cost flow. Min edge cost flow, in a way, charges for any non-zero amount of flow going through an edge. So you can say, well, if the flow here is 0, I don't pay for it, but if the flow is non-zero, I pay for it, and there's some capacity. So there's clearly a close relationship with all of these problems. Okay. Time for questions before I change gears?
But the problem you mentioned is still open. It could be polytype solvable, although the best you said it was a proof.
That's correct, yes. So for the preemptive case, I don't know of a proof that it's NP-hard. So we have a 2 approximation. We have the lazy activation algorithm, which works for unit length jobs. So our initial attempts were all trying to extend the lazy activation algorithm to deal with non-unit length jobs, but we couldn't get an optimal proof, any proof of optimality. Do you guys have any intuition about where it might go? I've thought about it both directions, so I don't know anymore. Okay. So let me talk a little bit about the non-preemptive case. We kind of punted that case. And I want to relate this to a problem that has been studied extensively in the literature. So I'll try to keep this part of the talk somewhat non-technical. So this is the busy time problem, where we again have jobs with release times, deadlines, and some processing times. But now we want to find a non-preemptive schedule. That's the main difference in this part. And the number of batching machines, which initially was assumed to be 1, in this line of work is basically assumed as an unbounded number, even though every machine has a batch capacity. And I'll explain that in a second. So let me jump to an example, which will make it clear. So here's an example of busy time, right? So here I have jobs with release times and deadlines. And these jobs all have some length, but I want to find a non-preemptive schedule this time. So this is what the input looks like. I have jobs with lengths, and I want to find a grouping of the jobs. So here is one possible grouping of the jobs, right? So I move the jobs around. That's the only flexibility we really have. And then we have to group the jobs. And we group the jobs in this way, where each group or a batch of jobs has the property that at most B of them are running at any point of time. So here, say B is 3. So I have at most 3 jobs running at any point of time. And so I've grouped them into 2 batches. And the cost of the first batch is the duration for which it is on, which is when does the first job start and when does the last job end. And then there's a cost for the second batch. And the goal is to minimize the total cost, right? But what I meant by this assumption of unbounded machines is that these 2 rectangles can actually overlap. And in the definition of the problem, of course, this is a fine schedule. Even one machine could run the schedule. Come on, do these jobs, turn off. Come on, do these jobs, turn off. But in the problem definition, this is not a constraint. So these 2 rectangles could overlap. So the sort of assumption is that a different virtual machine is being to run every batch. And that's sort of not a desirable part. And the work that I've been doing lately tries to address that, and we have some partial results in that step. Okay. So is at least the problem clear? It's just a non-preemptive version, really, with this caveat that things are unbounded. Okay. What's more interesting is that a very special case of this problem for interval jobs is also hard. So what is an interval job? An interval job is like the job on the top right, where there is no flexibility. The length of the job is exactly the gap between the release time and the deadline. Okay. So an interval jobs look like that. So you have no choice about when the job starts or ends. The job turns on at the release time, it ends at the deadline. So what is hard about it? It's kind of a stupid problem. What's hard about it? It's just the grouping that's hard. And this problem is NP-hard, even for interval jobs. Okay. So there's a paper by Winkler and Zhang in SODA 2003, which proves the NP-hardness of this problem, right? So all you want to do is to come up with the grouping, nothing else. Okay. So where are we? So the problem was proven to be NP-hard by Winkler and Zhang. A few months later, there was a paper by Alichari and Bhatia which gave a 2 approximation. And they gave an example that shows that their algorithm cannot do better than 2. And then there was another paper published 2 years later which gave a slightly different algorithm which also gave a 2 approximation of the same problem. And then a few years later, there was a 4 approximation published. So you say, wait a second, why are the bounds getting worse? They should improve. These authors were actually unaware of the previous work, that's all. Okay. Now, the algorithms all developed in all 3 papers are actually different. This algorithm, I would say, is the simplest of the lot. It's a very, very elementary greedy algorithm. So it's very easy to implement. And their algorithm's lower bound is 3, right? But because this greedy algorithm looks so simple, I thought it would be very easy to analyze it. So Koyel, Jessica, and I spent a long time trying to prove that this is actually a 3 approximation, but we failed in doing that. So I don't know where this greedy algorithm lies. After we failed, we actually discovered these 2 papers and realized that maybe even improving it to 3 wasn't that interesting because there were already algorithms with bounds of 2. Yes?
Is there any way to say anything about how these algorithms perform in practice?
Yes, so I have actually a high school student who's been working on implementing them, and the algorithms that do well in practice are sort of, I would say, small modifications of these algorithms. So you can provide some intelligence choices to these greedy algorithms, and those actually end up doing very well in practice. But these purely implemented, she never implemented this one, she implemented this one and that one. And most of the time this one really does quite well, but with some changes in the algorithm, right?
So the original
Yeah, the original algorithm doesn't do very well, but if you change it to do something more intelligently, in practice it does really well.
without improving the
Worst case bound, that's correct. Okay. So the story is going to get a little bit more interesting in a second, right? So this paper is actually interesting for a bunch of reasons, and I'll try to talk about that. So all of these results, by the way, are only for interval graphs, which was that very silly problem where you say, well, I have no choice as to when the job starts, so why is this even hard? So it's very frustrating that this problem is NP complete, because it's just the grouping that makes it hard. And then it's NP complete, and all these papers give, basically 2 approximation is the best bound. Okay. Now, what do you do when the jobs, the more general case, non-interval jobs? So there's a paper by Khandekar et al. Which gave a 4 approximation for this problem. And this is what their algorithm does. It's very interesting. It says that just assume for a minute that your batch capacity is unbounded. Okay? How difficult is that problem? They prove that that problem is actually solvable in polynomial time. Again, the solution is very complicated. It uses dynamic programming, complicated in the sense that the complexity is like n to the power 6 or something like that. So it's not very efficient. But you can solve this problem optimally. So what are you trying to do? You can move these jobs around in time, right? That's the only choice you have right now. Batch capacity is unbounded. As many things can run it concurrently. And you're simply trying to minimize the duration for which your machine is on. So you're simply trying to move things around so you minimize the projection on the x-axis. That's all you're trying to do. What they show is that you solve this problem for unbounded B, and you get this schedule. And now you treat these jobs as rigid interval jobs. So you basically adjust the release times and deadlines to snap around wherever the job got scheduled in that solution. And now you have an interval job case, and then they actually run the 4 approximation for the greedy algorithm by the Flamini et al. Paper. Okay. And then they prove that the final bound is 4. So this restriction doesn't really cost you anything, which is a bit strange. Okay. Now we looked at this and said, why are they using the 4 approximation? Now we discovered that there are 2 approximation nodes. Why don't we plug in a 2 approximation? That's a better algorithm, at least in terms of the worst case bound. It turns out that that doesn't quite work. So what happens is when you do this adjusting of these jobs, the optimum schedule can actually jump quite a bit, right? But the greedy algorithm is oblivious of the optimum schedule. It just bounds things based on the sum of the processing times of jobs, which never changed, right? So there is a benefit to that analysis of the greedy algorithm. So what we were able to prove is that even if you plug in the better 2 approximations, once you've done this first step, the optimum solution might jump by a factor of 2, and then when you apply a 2 approximation, you can end up with a solution which is 4 times the optimum. Okay. So no matter which route you go, you are ending up with the 4 approximation. You could solve the problem the way they did by doing the dynamic programming and then run the greedy algorithm. You get a bound of 4, but you could now plug in a 2 approximation and you're not getting anything better because the optimum solution jumped, right? And we actually have examples where the optimum solution jumps and you apply that algorithm, you get a bound of 4. Okay. So what do we do? So now our final result is a bound of 3 for the general problem. And our bound is 3 for interval graphs, for non-interval case, everything is 3, okay? So it is a better bound. So how does our algorithm work? The first step is still the same. We solve the dynamic program for unbounded B and then get an interval case. And now our greedy algorithm is a little bit more sophisticated. So their greedy algorithm does the following. It simply sorts jobs by decreasing order by length. So they want to worry about the long jobs first. And then basically it's like a trivial bin packing algorithm. They start stuffing the jobs in batches, and then when putting a job in a batch will exceed the batch capacity, they create a new batch. So it's a very simple algorithm, right? So we're going to do something slightly more clever. So we have a large collection of interval jobs now, and we want to decide what the first batch is going to be. Now remember, their algorithm just orders the jobs in length and does one job at a time. We're going to do something slightly more sophisticated. So our goal is to find a subset of disjoint jobs. So in this case, this red set of jobs is a disjoint collection of jobs. And which subset of disjoint jobs do we want to find? We want to find a subset of maximum total length. Okay, so this is, if you look at the Kleinberg-Tarrados textbook in the dynamic programming chapter, in the greedy algorithms chapter, this is known as the weighted interval scheduling problem, right? So there's a very simple dynamic programming solution for this problem, weighted interval scheduling. So the whole goal is simply to find a collection of disjoint jobs of maximum total length. And this algorithm we call greedy tracking. And this disjoint collection of jobs will give you the first track in the batch. And then on the remaining collection of jobs, we apply the same algorithm again. Right? We find another disjoint collection of jobs, make that the second track. And once I have filled up B tracks, that's my batch, and I'm done with the first batch. And then whatever jobs are left, I'll apply the same algorithm every time. So I'm finding this disjoint collection of jobs at every step. Okay. Now this algorithm.
So this is like coloring with B colors, right?
Yes.
But that you can do in one shot. Do a kind of a weight.
But here the cost function is a bit different. In the end, I'm going to look at the. So look at this example, right? So if I pick the first track, which are the top two jobs. Now here all the jobs are the same length, right? So, and the example is set up in a way that there are no three disjoint jobs. So the first track is the first two jobs. Then the second track could be these two jobs, and that's my first batch, the first two. And then track 3 creates a new batch, it's these two jobs, and track 4 goes with track 3. So notice that my cost is actually pretty high because I'm basically turning this batch on here, it goes all the way to the end, then I'm turning this batch on here, it goes all the way to the end. Now anybody looking at this picture is going to say, wait a second, track 1 and track 3 should have been merged together, and then track 2 and track 4 should have been merged together. And our algorithm is not taking benefit of any alignment issues. We just union the tracks, and that's where you're sort of paying a price. It's not exactly answering your question, but I'm just trying to illustrate even our algorithm, we have an upper bound of 3, and this is the example that we have that shows a lower bound of 2. Right? So the right analysis is somewhere between 2 and 3.
I'm just asking, instead of repeating your finding a weighted color class
At every step.
At every step, do for B steps, do it in one shot.
Maybe that will give a bound of better bound. I don't know. We didn't think about that. But you're saying that somehow that will. But how do you take the overlap cost into account, right?
How do you take it?
We don't. That's why we're paying this penalty of 3. Right? So even in this example, we are not overlapping anything.
Right.
Track 1 and track 2 get union into one bundle, and track 3 and track 4 get union into one bundle. And that's not optimal. If I put track 1 and 3 together, that's a much better alignment.
But you can merge this. You can merge two tracks only if they're completely identical.
No, in our merging, it's oblivious. So the first B tracks go into the first batch. The next B tracks go into the next batch, and so on. And even that works, right? But so it improves a bound of 4 to 3, but I think the right answer is 2. And it's quite likely that some clever way of doing track merging. So if you go back how we are finding these tracks, right? So Seth is right. So we are finding one sort of color class with maximum weight, and then with whatever the remaining jobs are left, we create the second track. But you're saying that we should have actually found B of them simultaneously.
You can do that and maximize the total weight. That you can do in polynomial. Finding maximum.
But I don't know whether it will help in this example actually, because why would that prevent track 1 and track 2 sort of being paired together? It won't, because track 2 and track 3, the only difference is the overlap issues with track 1, and your objective function somehow isn't modeling that, right? So I believe that that's where the improvement needs to come from. So I don't know whether it will be of much value to solve that problem. That's all. I just don't know. Okay. So in terms of the actual proof, here's sort of the key lemma which underlies all of the analysis. And I won't go through the analysis, but I want to at least mention this lemma. So we are able to prove that at every step, when you find this maximum disjoint collection of jobs, what we're calling a track, it has the property that its span, or the total cost of the track, is at least 50% of all of the remaining jobs, right? And this lemma is sort of the key to doing the whole analysis about comparing to the optimum solution. So I'm not going to spend time going over the proof. The proof, at some high level, follows the greedy proof at this point in terms of a high level charging scheme. Of course, the proof is actually different because the algorithm is different. But it's sort of a standard charging proof. I wouldn't say it's anything very sophisticated. Let me start by saying, so there's a student who's been actually implementing some of these algorithms and trying to compare them. We don't have any real data sets, right? So all of this comparison on synthetic data sets. Like I mentioned earlier, in this dynamic programming solution, there's a lot of inefficiency in terms of running time in mapping the general case to the interval case. So again, now we have some algorithms that at least do this efficiently, but at a cost to the optimum solution. I didn't really get a chance to talk about this result, but that's fine.
What's the online model?
Oh, so the simplest online model is the jobs are available when they are released. And actually, we have an algorithm where if B is infinity, so you have sort of this very powerful machine that you can turn on whenever you want, and whatever is in the system gets run, but it's a very expensive machine to run. So you want to minimize the time for which you run it. And in the online setting, we have a 5 competitive algorithm. So the algorithm is very simple. You delay things as much as you can, so you never turn it on until you are about to be in a situation where if you don't start the job, you're going to miss the deadline. So you start the job at that point, and let's say this job has some length, 13, then we're going to commit to turning the machine on for twice the length of the job, right? So everything else that is available as that machine is running, that fits in that window of time, will get executed. And then you turn the machine off. Unless some other job is also about to miss its deadline, then you start that. But the main thing we commit to is when we run a low job, we double the commitment to how long we're going to run it for. And so at least for that algorithm, the upper bound and lower bound of 5 are tight. We have examples where the algorithm does 5. Again, I don't believe that that's the right algorithm. So I think there'll be improvements possible to that algorithm.
So is that like price efficiency for like HDN side or like batch? I'm not sure if you're familiar with Azure.
No, I'm not.
Okay.
I didn't answer the question actually.
Okay.
Maybe we can discuss it offline. Right. So I alluded to a lot of results in this talk. So let me just quickly go over these slides. So the paper that I spent most of my time talking about lazy activation, actually I only covered one algorithm of the paper. The paper actually has several results. That was in ESA 2012. And then we had an experimental analysis of some of those algorithms of capacitated covering and also of the general length problem in LNX 2013. And most of the stuff with busy time and also the preemptive case was published in a more recent paper in SPAR 2014. And I didn't really get a chance to talk about the work with Frederick. The stuff that I mentioned very early on was a paper by Barna, Jian, and myself, which was published in SORA 2010 with this machine activation problem. And then there are some generalizations, and then these are some of the papers that I cited in the talk. I also went to show you pictures of my collaborators. So Barna Saha graduated with her PhD. Now she's a faculty member at UMass. Jessica Chang finished her PhD a couple of years ago, is now at Department of Defense. Jian is now a faculty member at Tsinghua University. Koyel is at Xerox Labs. You were asking about Hal Game earlier. He's Professor Emeritus at Colorado. But he does still read email, and he's been actually pretty hard at work in his retirement. So one of the things that he told me is that he had a bunch of conference papers that he never published in journals. And so he's been spending a lot of time writing like 40-page long journal papers of stuff he published in conferences a long time ago. So, and he sent me some of them to read. I just didn't have time to read them. But very interesting work. And actually, I didn't get a chance to talk about some of the things he did in the ESA paper, which are very interesting. He developed some combinatorial algorithms for stuff where we were solving linear programming initially. And Frederick Kohler is actually an undergrad at Princeton. I started working with him when he was in high school in Maryland. And so we've continued that collaboration. So let me take a few more minutes and talk a little bit about some stuff that has been the focus of attention of both myself. And the back of the room is the inventor of Skipless, Bill Pugh, who's Professor Emeritus at UMD. And from starting about a year ago, we've been hard at work at a building project. So I wanted to just talk a little bit about the department. The department has over 50 faculty, much larger when you consider all the affiliate faculty in the various affiliate schools. Undergraduate enrollment in computer science is booming all over the country, but especially at Maryland. We went from 1,000 majors to 2,200 undergraduates just in the last 36 months. We have about 250 minors and about 400 computer engineering students. So let's talk a little bit about looking ahead. So I know HoloLens is a big exciting thing happening here at Microsoft. One of our alums, Brendan Uribe, together with two of his friends from Maryland, Michael Antonov and Andrew Rees, were co-founders of a company called Oculus VR, which was big time in the news last year when they got bought by Facebook for $2 billion. And so Brendan and Michael have done an amazing gift to kick off this project that Bill and I have been heavily involved in. So that's sort of the picture of the model of the building that we're in the middle of. planning. It's a 6-floor building for computer science. A lot of facilities for lecture halls, collaborative classrooms, big open cafeteria, research labs, lots of space for PhD students. I guess our undergrads who've been sort of stuffed like sardines in classrooms lately would love those facilities. Ryan sitting at the back there is an example. And especially for PhD students, the current building that we are in is kind of depressing. None of their offices have windows and lights. And so this building would be an amazing facility for students to come together and collaborate and work together. So I just wanted to share with you sort of the ground floor building model. So we've been working with the architects for the last 6 months or so. So that's sort of the extension that was in the picture before. So this part is going to have both a 100-seat collaborative classroom as well as a 300-seat collaborative auditorium. The main building itself, that's sort of the footprint. It's a boomerang-shaped building. This is the open cafeteria, atrium space. And then there are going to be lots of research facilities, labs. The first 2 floors are primarily for undergraduates with classrooms, robotics labs, and so on, as well as hacker-maker spaces, which occupies actually a third of the fraction of the second floor. And then floors sort of 3, 4, 5, 6 are mostly for research and PhD students. So that's been a pretty exciting project that we are in the middle of fundraising for. So you sort of asked me earlier what brings me to Seattle. So we have about 90% of the money in place. The state of Maryland is funding about $100 million. Brendan and Michael together gave $35 million. The cost of the project is expected to be about $148 million. So we're still about 12 to 13 million short. So that's what we're fundraising for. But the building project is a very fast track. The plan is to do a groundbreaking next year. So I guess the architects have to finish their plans this year. And opens in 2.5 years from now. So come visit.
Where is it going?
It is going next to the CSIC building. So if you look at this model carefully, that's the CSIC building, and this is a big parking lot right now. So as soon as you enter Campus Drive from Route, from Campus Drive, this will be the first big thing you'll see on the right-hand side. Actually, very prominent from Route 1.
It's going to stay there. It's going to literally replace the parking lot.
Yes.
On the,
And in fact, the whole parking lot will go away, and this area will all be landscaped.
and there's a stream there that goes.
That's right, the stream right here.
Okay.
That's actually the reason why you see part of it doesn't go all the way down to the ground.
Yes.
100-year floodplain, so we can't actually build in that area on the first floor.
Got it. Okay. And that's an overhang?
Yes, that's an overhang.
Well-
This will be a covered seating area. That's the
We
current
were
plan.
hoping to do a pure cantilever. Turned out that was going to be a little bit too expensive, so there'll be some pillars there to help support the.
Okay. Interesting.
But that'll be a plaza that will be covered by the rest of the building. Be another part of that. But yeah, the whole area will be. This will be a new quad. You know,
Yeah, it's
people
very
playing
close to-
frisbee and hanging out on the.
Right,
grass.
lots of outdoor space, the cafe. And also, if we want to organize conferences here, this will be amazing, at least for a 300-seat size conference. And it's sort of,
The hotel across the
and there'll be a
street,
new hotel
the
coming up
center.
next summer across the street. So that hotel project started a while ago. Actually, there's already stuff in the ground. So they'll open well before us, I think. Certainly by January 2017, I think they'll be open. And that's just like 100 meters away. But yeah, I mean, it'll be a great place to host events because this sort of separates the noise from the rest of the building and so on, right? So you can actually have an event here and it doesn't disturb the other occupants of the building. What else? So in terms of the department, these are sort of some of the areas that we are planning on growing in. The plan is to hire about a dozen new faculty in the next 3 years. So going to be a lot of faculty positions. Along with Brendan, his mom gifted 2 chairs for computer science. So we're going to be recruiting for a chair in the specific area of virtual and augmented reality. There's already a lot of activity in cybersecurity actually in Maryland with the cybersecurity center that opened about 3 years ago. But our plan is to grow that. There's a new quantum computing institute. Andrew Childs from University of Waterloo was recruited about 8 months ago. So he joined Maryland and we're looking for a second faculty member in that area. And these 3 areas are sort of big growth areas, I would say, in the next 3 years.
Don't see theory and algorithms on this list.
Well, the quantum computing is really almost everybody in that space is a theory person, at least the ones that we are trying to go after. Andrew's a theory person, for example. Andrew Childs, yeah. So he got his PhD in physics, but most of his publications are, he has several papers in the theory conferences, for example. He was a professor at Waterloo for a number of years before we recruited him. Another exciting thing that's been going on is CS Education for Tomorrow. This was actually funded by a gift from Bill Pugh. And this is sort of twofold. We're trying to improve the quality of the education for our students. Part of this involves creating flipped classrooms. So a lot of the faculty have taken this model on where lectures are videotaped. So there's a video lab set up now. So if you're teaching any class in Maryland, you can just come to the video lab, record the lectures in advance, so that students can watch the lectures, and then the classroom can be actually discussion as opposed to just teaching. We just recruited a special honors advisor whose goal is to do CS enrichment for undergraduates, so different from advisors. This was a person, Rich Gabow, who used to be a professor at Maryland and left to go to Italy 15 years ago. We just recruited him back. We're also creating a data science graduate certificate program, which will launch next year. This is a 12 credit program with 4 courses. And we're in the process of creating an undergraduate data science specialization as well. So this will be similar to the cybersecurity specialization, which is the only specialization we have right now. Okay? That's it. I think I'm out of time, so let me stop.